Okay, I don't like to spend a lot of time on the theory. I like to focus on application, but do need to spend a little bit of time. So let's talk about the limit of a sequence. So a sequence defined by a sub n has the limit L, or converges to L, and we denote this as the limit of the sequence as n goes to infinity equals L if for every epsilon greater than 0 there exists a positive number n such that the absolute value of a sub n minus L is less than epsilon whenever n is greater than a particular n. Now, if such a number does not exist, then the sequence has no limit, or it diverges. So I just wanted to draw you a picture here. Basically, this statement here, what it really says, it just says that there's some number out here somewhere. There's some number out here somewhere, call it n, such that once you get terms greater than that number, or terms farther to the right than that number, then all of the terms will fall within the L plus epsilon and the L minus epsilon band. So basically, like for instance, when you first start this sequence, you might have a term outside of the band, and then a term right on the border of the band. But then if at some number here called n, if once you get beyond that particular number, if all of the terms stay within that particular epsilon, this particular epsilon band right here, then the limit exists, and the limit is actually going to equal this number L. Now, if this sounds familiar, it's because we have a very similar definition when we talked about when the limit of a traditional function equaled L as x goes to infinity. Now, on the other hand, if we say the limit of the sequence as n goes to infinity, that means for every positive real number p that there exists a number n such that the sequence will be greater than all of those numbers when n is greater than n. So basically what that means is that there's a term out there somewhere where all the terms will be greater than any positive real number that you could come up with. And so that just means that the limit of the sequence goes to infinity. And there's a similar statement to be able to say the limit of a sequence goes to negative infinity. Now, this theorem kind of relates the sequences to functions. So let me show you how this works. Let's say that you have a sequence of a sub n, and we'll say that f of n is the nth term. Now, suppose we have a function f of x that exists for every real number greater than or equal to 1. Okay, well then we can say if the limit of the function as x goes to infinity is L, then also the limit of the sequence as n goes to infinity must also equal L. So, and another way to say that is just to say it this way: the limit of the sequence a sub n as n goes to infinity is L. Okay, now also if the limit of our function goes to infinity as x goes to infinity or negative infinity, then the limit of our sequence as n goes to infinity equals infinity or negative infinity. So moreover, we can just say the limit of the sequence as n goes to infinity is infinity or negative infinity. So let me show you an example here. So let's say that I have a sequence defined by this term, the nth term 1 plus 1 over n. Okay, now let's determine if this sequence converges or diverges. So since that's our sequence, then we'll say f of n is 1 plus 1 over n. And let's consider the function, the traditional function, f of x equals 1 plus 1 over x. Okay, now you can easily show that the limit of this function is 1. And I'll go ahead and write that out for you here in just a second. Okay, so I didn't write the little n goes or x goes to infinity here, but just assume that's underneath the limit notation. So the limit of 1 plus 1 over x can be written as the limit of 1 plus the limit of 1 over x. And of course, as x goes to infinity, the constant just goes to 1. And as x goes to infinity here, 1 over x goes to 0. So that limit of 1 plus 1 over x as x goes to infinity would just equal 1. So that's pretty easy to show. And since that's true, then by that theorem that I just showed you, then the limit of this sequence as n goes to infinity would also equal 1. So therefore we would say the sequence converges to 1. So let's do a couple more here. Okay, so on this first one, the sequence is 1/4 n squared minus 1. And so let's consider the function 1/4 x squared minus 1. And now let's find the limit of this function as x goes to infinity. Well, it's pretty easy to show here that as x goes to infinity, you'll have 1/4 times infinity squared minus 1, which is just infinity. So therefore, by the theorem, then this limit, the limit of this sequence must also be infinity. So therefore it has no limits. So therefore the sequence must diverge. Okay, now here's another one, and this is -1 to the n minus 1. And on this one, I'll just write out some terms to show you. So let's say if n is 1, then you'd get -1 to the 0 power, which is 1. And then if n was 2, you'd get -1 to the first power, which is -1. And then if n was 3, you'd get -1 squared, which is 1. And then if n is 4, you get -1 cubed, which is -1. And so now you should be able to see what's happening here. This particular function is simply oscillating back and forth between -1 and +1. And so therefore we can deduce that it has no limit, and so therefore it must diverge. Okay, so now I want to find the, I have the sequence 5n over e to the 2n, and I want to determine if that sequence converges or diverges. So let's consider the function 5x over e to the 2x. So what I need to do is I need to try to find the limit of this function as x approaches infinity. Okay, well, if you tried to evaluate this directly, you would get 5 times infinity, which is infinity, and then you would get in the numerator, and then in the denominator you get e to the infinity power, which is infinity. So this actually is the indeterminate form infinity over infinity. But what we can do now is we can apply L'Hopital's rule. So you just take the derivative of the top, which is 5, and then take the derivative of the bottom, which is 2e to the 2x. And then it's relatively easy to see that if the numerator stays constant, and as x goes to infinity, the denominator goes to infinity. So with the numerator constant and the denominator going to infinity, then this limit is actually going to go to 0. So therefore, since the limit of that function goes to 0, then so must the limit of that sequence go to 0. So that sequence converges to 0. This next theorem is important in determining the convergence or divergence of certain sequences. So it says that if you have the limit of a real number to the nth power as n goes to infinity, that's going to equal 0 if the absolute value of that number is less than 1. And then it's going to go to positive infinity if you take the limit of the absolute value of that number to the nth power. That's going to go to positive infinity if the absolute value of r is greater than 1. Okay, so let's see how we can apply that here. All right. In this particular example, we have negative 2/3 to the n. So what we need to do is we need to see what is the absolute value of negative 2/3. Okay, well that would be positive 2/3, and then we have to say, okay, is 2/3 less than 1 or is 2/3 greater than 1? Well, since 2/3 is less than 1, by this theorem, it must converge to 0. And then the next sequence, I have 1.01 to the n. So in that case, look at the absolute value of 1.01. Well, that's just going to be 1.01, and it's greater than 1. Now, it's not much greater than 1, but if it's greater than 1, then that sequence must diverge. So that sequence diverges to infinity. Now on this third one, I'm going to use a little trick that we used for functions. So here I have the limit. I want to find out if this converges or diverges. So I want to find the limit of this as n goes to infinity. Well, you know you'll have infinity over infinity if you do that, which is an indeterminate form. The one way to attack this is to just divide every term by n squared. So if I divide the top by n squared, I just get the limit of 2. And if I divide the terms on the bottom by n squared, I get the limit of 5, and then minus 3 over n squared. Well, on the top I know the limit of 2 is just 2, and on the bottom the limit of 5 is just 5. But 3 over n squared, as n goes to infinity, that must go to 0, so I get 5 minus 0. So this actually converges to 2/5. Now I could have used L'Hopital's rule on that, but it wasn't really a function, and even though you can use L'Hopital's rule on sequences, I didn't want to throw that at you yet. Okay, just a quick note, limit theorems with sequences are actually analogous to those used with functions. So for instance, since the limit of the sum of two functions are equal to the sum of the limits, then the limit of the sum of two sequences is equal to the sum of those limits, and so forth. Same thing with a product, and so forth. So they're basically the same as limits with functions. A couple notes here. If your sequence is a constant, then the limit of that sequence is just going to be the constant. In other words, it's not going to go anywhere. If you remember that other one I had, that constant sequence I had earlier, that was 4, and every term after it's going to be 4, so it's just going to go to the constant 4. So it's not going to matter how many terms you go out, you're still going to get 4. And then this example here says that if a sequence is a constant over n to a power, where k is some power, then the limit of c over n to the k as n goes to infinity is always going to be 0. So for instance, here I have the limit of 5 over n to the 2/3 power, and obviously 2/3 is a positive rational number, so the limit of that as n goes to infinity is actually going to equal 0. Okay, so I just wanted to make sure I showed you an example of that. Okay, so this video is going to have to be shut down right here, and I'll pick back up on the sandwich theorem in the next video.